The central limit theorem puts a name to a phenomenon that we've been talking about already, wherein the sampling distribution of the sample mean, x bar, is approximately normal. However, this only holds if the sample size is sufficiently large, typically greater than 30, unless that distribution of values from the population is especially skewed. So, looking at a frequency distribution of the values x in an underlying population, while potentially not normal itself, the distribution of sample means will be approximately normal. And we see that the population mean, mu, is equal to what we call the mean of sample means, mu sub x bar. However, the population standard deviation, sigma, is not the same as that standard deviation in the sampling distribution, but it is related in that the standard deviation of that sampling distribution is equal to the standard deviation in the population divided by the square root of sample size. Sigma divided by the square root of sample size is also called the standard error of the mean, or SEM for short. Recall that for individual values x, the z-score is equal to x minus mu divided by sigma. But when working with a distribution of means, the z-score is calculated as x bar minus mu divided by the standard error of the mean. As an example, let's again consider human body temperatures. The population mean is 98.6 degrees Fahrenheit, and the standard deviation is 0.62 degrees Fahrenheit. We'd like to know the probability of an individual having a body temperature of 98.2 degrees Fahrenheit or lower. We need to calculate the area under the curve. To do this, we convert our x value into a z-score and look up that z-score in a table of cumulative values from the left to the right. This tells us that the probability of a body temperature 98.2 degrees Fahrenheit or below is 0.2578. But because we were looking up the value for a rounded z-score, this is not exact. If we use the norm.dist function in Excel to calculate the exact area under the curve, we get 0.2594. Now, what if we wanted to know the probability of getting a sample mean of x bar? For example, conducting a study of 106 participants and finding that mean value to be 98.2 degrees Fahrenheit or lower. To do this, we need to look at the sampling distribution of x bar. Now, the mean of sample means will be the same as the population mean of 98.6 degrees Fahrenheit. However, our standard deviation changes and is calculated as the population parameter divided by the square root of sample size. For all of our samples x bar, that sample size is 106, so the standard deviation is 0.62 degrees Fahrenheit divided by the square root of 106, which is 0.0602 and then some. So if we want to find the probability of obtaining a sample mean of 98.2 degrees Fahrenheit or lower, we again calculate the area under the curve, which is much less now that we're using the standard error of the mean when we calculate our z-scores. This puts us much further away from that mean of sample means, where the probability of obtaining a sample mean of 98.2 degrees Fahrenheit or below is almost ridiculously low.